Okay, good afternoon, everyone. So I am Toshihiro Tsuyama. I belong to Department of Materials in Kyushu University, and I am one of PIs of I²CNER today. So I will be your host. So now let me introduce today's speaker, Professor Dr. Kaneaki Tsuzaki. Okay, Dr. Tsuzaki is a Professor Emeritus of Kyushu University and Emeritus Fellow of NIMS. He has started his career of steel research in 1976 when he became a senior of the Department of Metal Science and Technology in Kyoto University. Then he completed the doctoral course in 1983 and worked as a postdoctoral researcher at MIT in the same year. And he became an assistant professor at Kyoto University in 1985 and an associate professor at Kyoto University in 1991. And he moved to the National Research Institute for Metals as a unit director in 1997. And then he joined Kyushu University as a professor of mechanical engineering division in 2013 and named distinguished professor in 1916. After retirement from Kyushu University, he returned to NIMS and named NIMS Fellow. Then he retired and was named NIMS Emeritus Fellow in April 2025. And he has mentored a very large number of students in his life and has sent many outstanding steel researchers into the world. And of course, he is still active and loves steel and microstructure in research and education. So these are the biographies of Dr. Tsuzaki. So before we begin, I would like to take a moment to remind you that your questions will be addressed after the presentation. Please use raise hand button or type your question or comment in the Q&A box. When you are called on, please unmute yourself. Okay, this webinar will be recorded and made available on the I²CNER website. So now everyone, please welcome Professor Dr. Kaneaki Tsuzaki. So Tsuzaki-sensei, please start your presentation.
Okay, thank you very much, Professor Toshi Tsuyama, for your kind introduction. Good afternoon, everyone. Thank you very much for the opportunity to give this lecture in the third I²CNER seminar in 2025. So the title of my talk today is Phosphorus doping works well for fracture resistance in high-strength steel, a case of elongated grain structure. The co-authors of this presentation are Moronaga-san and Kimura-san. Phosphorus, an embrittlement element in steel, can also be used as an effective element if the microstructure of a steel is controlled. This is the message of my talk today. Agenda. 1. Background and motivation. 2. Seasoned ideas. 3. Challenging impact toughness. 4. Challenging hydrogen embrittlement. 5. Related Japanese steel research project. And 6. Concluding remarks. Background and motivation. We need high-performance steel for sustainable society. So we need high strength along with good formability, good machinability, good weldability, high toughness, high fatigue limit, etc. And today's topic is toughness and embrittlement. This is a textbook of Professor George Klaas. Chapter 19 of this book discusses low toughness and embrittlement phenomena in steels. And on page 382, it is written that toughness is the term used to describe the ability of a steel microstructure to restrict rupture. Embrittlement implies the processed microstructure condition that creates lower toughness than expected of a steel. Today's elemental protagonist, the main player, is phosphorus. In the periodic table, phosphorus is located below nitrogen. It is well known that phosphorus P, a chemical constituent of steel in JIS standards, is treated as one of the harmful elements affecting low temperature, impact tough, low temperature, brittleness, weldability, cold workability, and impact toughness. Thus, for example, the maximum P content in JIS SCM 440 AISI 4340 is strictly specified as 0.030 weight percent, 0.054 atomic percent for safety. Here is Professor Krauss's textbook again. Chapter 19 describes many embrittlement phenomena. In the eighth of these, the embrittlement by P is written. The eighth is tempered martensite embrittlement. On page 398, we can find a figure like this. The vertical axis is Sharpie V-notch impact absorbed energy at room temperature, and the horizontal axis is the tempering temperature. The result for two 4340 steel with different P content levels are shown. In both steels, tempering in the range of 200 to 400 degrees Celsius doesn't increase the energy like this. This is tempered martensite embrittlement, which is related to cementite precipitation occurred during tempering. Excuse me. The embrittlement is enhanced by P doping like this. And as shown in the right figure, fracture structure is characterized by intergranular fracture along prior austenitic grain boundaries. This declaration has been attributed to segregation of phosphorus to grain boundary during heat treatment and the resulting reduction in cohesion. For this amount of 0.0% P, if you go back to the two previous slides, you see that the 0.03% is the maximum P content in JIS SCM 440, AIS 4340. This fact and the result shown in the Professor Krauss's text led me the following question. Question is, how does toughness change when P is greater than 0.03 mass percent? I wanted to know the result for high temperature tempering above 500 degrees Celsius, where the impact energy rises. I believe you all would like to know too. So I did. Here is the result. Only phosphorus content was varied in SEM 440. The tempering temperature in this case was 550 degrees Celsius, and the tensile strength was 1100 MPa. The impact energy at room temperature shows more than 90 joule when the P content is 0.001%. And the fracture surface shows dimple fracture. And impact energy decreases markedly with increasing P content like this. At 0.093% P, almost complete intergranular fracture is observed. Here, I should say that even after high temperature tempering, embrittlement due to P is still pronounced. We also did an OJ electron spectral analysis to confirm the segregation of phosphorus at grain boundary. In the grain boundary fracture area, we observed about 3 atomic percent P, which is 40 times the average value. The lower content of P at number 10 and 12 shown in red square corresponding to cleavage fracture region like this. Interestingly, these regions also have a high phosphorus content of 1 atomic percent or more. Based on the knowledge and background I have described so far, here I'd like to do a vertical Q&A on phosphorus and toughness. First question, phosphorus is an embrittlement element for steel, isn't it? You will answer, sure, it is a common sense in the field of steel science and technology. Second question, can you make a steel tougher by phosphorus? Your possible answer is no, we cannot. We can make a steel stronger by phosphorus. This is solution hardening by phosphorus. However, toughening by phosphorus is impossible since phosphorus is an embrittlement element. Therefore, toughening of steel by phosphorus is a challenge. So it was a long introduction on background and motivation. Next up is theories and ideas. How to improve toughness of a high-strength steel by the embrittlement element phosphorus, P. Let me briefly describe our scenario according to Professor Cohen's reciprocity diagram. Processing is temp-forming. Structure is ultra-fine elongated grain structure. Properties are high toughness and strength. And performance is safety and eco. Our sheath and idea is in the use of delamination toughening. We published a research study in 2008 with this title, Inverse Transformation, Inverse Temperature Dependence of Toughness in an Ultrafine Grain Structure Steel. Here are the main results. steel is 0.4 carbon, 2 silicon, 1 chromium, and 1 moly, and tensile strength is 1800 MPa. The QT material shows a normal ductile to brittle transition with low impact energy values as shown here. However, for material subjected to temp forming TF, the method of which will be shown in more detail later, the impact energy is higher. And as you can see here, impact energy increases with decreasing test temperature. In this temperature range, delamination was observed as shown in the bottom picture. This is the microstructure of TF. The microstructure is characterized by elongated grain structure along RD loading direction, 260 nanometer grain size along TD transverse direction, fine carbides smaller than 50 nanometer, and strong 110 parallel RD deformation texture. We have studied the mechanism of delamination toughening, interaction between weak interface and stress sigma SD striking direction that is generated by plastic constraint at the notch root can make delamination. When the delamination with a crack arrestor geometry occurs, as shown in the left figure, the triaxial tensile stress state is relaxed toward a uniaxial tensile state, which lowers the DVDT and increases the impact energy. This means that we can use brittle structure to enhance toughness in ultra-high strength steel with an anisotropic structure. What kind of an idea will come out of this? Yes, this idea. We can use an embrittlement element of phosphorus to assist delamination. Next, the challenge impact toughness by P-doping is presented. The steel used is SCM440. Only P content was changed from 0.001, 0.018, 53, 68, and 0.093 mass%. The main process is multi-pass caliber rolling at 500 degrees Celsius, namely warm rolling of tempered martensite. The total reduction area of 78% produced a bar with a cross-section area of 14 millimeters square, and the bar was finally annealed at 550 degrees Celsius for 1 hour. Again, this slide shows the microstructure development along with processing. Before processing, martensitic microstructure is isotropic. and the rolling at 500 degrees Celsius creates an ultrafine elongated grain UFEG structure. This is anisotropic. We call this process warm tempering. And I'd like to point out here that Professor Imao Tamura was the first to call the deformation of tempered mountainside temp forming in 1963. This slide shows microstructure of QT and TF sample in 0.093% P, the highest phosphorus content. In TF sample, elongated fine grain along the loading direction are seen. Inverse pole figure shows a strong 110 parallel RD fiber texture. The SCM microstructure of TF shows the carbides are spherical and aligned in the RD direction. As mentioned earlier, the carbides aligned on grain boundary are also a factor in delamination. One thing to note here, although the microstructure are not shown on this slide, P addition up to 0.093% does not show significant effect on microstructure of the QT and TF samples. Next, phosphorus content effect on tensile strength is shown here. Stress and P content. The P addition up to 0.093% doesn't change the tensile strength of QT and TF sample both like this. It is reasonable since the microstructure isn't affected by P doping, as I said in the last slide. Note again, the final heat treatment temperature was 550 degrees Celsius for all. Now, this slide shows the result of the impact test that you have been waiting for. As shown in the introduction, the impact energy decreases monotonically with increasing P content in the QT material, like this. On the other hand, in TF material, impact energy increases as P content increases, especially at P content more than 0.05%. In the TF 0.093% P still, significant delamination occurs as expected. Tsujiyama-sensei, is it okay?
Yes, no problem.
Anything wrong? It's all right? Okay.
Yeah.
Okay, let me continue. So this slide, number 26, shows fracture surface of the 0.093% P steel. The intergranular fracture occurred along the boundary of the prior austenite grains of the QT sample. In B and C, you can see SEM micrograph of delamination plane of the TF sample. Fracture mode of the delamination planes is characterized as a mixture of phase-side cleavage and intergranular fracture indicated by arrows like this. Now that you have seen the results so far, you may have these questions. Q1, what is the effect of the P content on the absorbed energy when the delamination doesn't occur? Q2, does the delamination occur even in the 0.001% P steel, high purity steel? And Q3, what is the relationship between delamination and phosphorus segregation? To answer the Q3, EPMA mapping on the fractured sample may be effective. But what should we do to answer the Q1 and Q2? The clue is on the previous slide, number 17. As shown here, delamination doesn't occur at high temperatures and is accelerated at low temperatures. Therefore, to answer to question 1, we can do the impact test at high temperature. And to answer to Q2, we should do the test at low temperature. So all we have to do is to get the Sharpe-Foot curve of the impact energy of the TF and QT sample with different P content. Here, Sharpe-Foot curves of temp-forming TF and quench and tempered QT samples with different P content. 0.001% P, 0.053, and 0.093% P. You can see here the absorbed energy of the upper shelf without delamination decreases from 180 to 120 joule as P content increased to 0.093%. This is the answer to question 1. Here, you may have a further question. Q4. Why do temp-form samples shows higher energy even without delamination upper shell portion? I think that the reason must be associated with the strong 011 RT texture and the unique carbide arrangement in the microstructure. I'll further discuss in the discussion time if you want. But now we need to concentrate on question 2. Does the delamination occur in the 0.001% P steel? The answer is yes. It was found at the low temperature here. I show you the delamination occurred at -150 degrees Celsius in 0.001% P TF steel. Here, there is not significant segregation of P. And so the possible factors for weak interfaces are 001 cleavage plane aggregate, carbide arrangement, unique arrangement, and maybe also manganese segregation bands. I should note that the yield strength at -150 degrees Celsius is much higher than that at room temperature, where the applied stress is the driving force for delamination. I think we have almost solved Q1 and Q2. How about you guys? Okay? So now let's go on to Q3. To answer the Q3, we did EPMA mapping on the fractured sample. Oh, click. This slide shows the crack propagation on EPMA mapping in 0.093% P steel at minus 20 degrees Celsius. First, I should note again that QT was treated after the temp-forming of 78% in deduction. For this reason, wide phosphorus segregation band along the RD direction are observed in the QT samples as well. In the QT sample, the cracks propagated along prior austenite grain boundaries, which isn't influenced by phosphorus segregation bands as shown here. Lower phosphorus lesion and high phosphorus lesion doesn't matter. G's phosphorus segregation band must be strongly related to solidification segregation. On the other hand, the EPMA mapping on the TF sample shows that delamination cracks preferentially initiated in and propagated along the phosphorus segregation bands like this, like this, like this. So, microstructure control from solidification is necessary to optimize the improvement of impact toughness by p-doping. This is another example of EPMA mapping on 0.093% PTF steel at minus 20 degrees Celsius, showing the delamination cracking related to the phosphorus segregation bands, like this. On this sharp beautiful curve, I'd like to emphasize that phosphorus assists delamination toughening in a wide temperature range. This slide is a case of a delamination crack at room temperature. So then we make tentative conclusion for impact toughness. Answer to the question in introduction I made. Can you make a steel tougher by phosphorus? Answer should be, yes, we can. We can make a steel stronger by phosphorus through delamination toughening in ultrafine elongated grain structure. This is a case study of positive use of an embrittlement element of phosphorus in steel through microstructure control. Now move on to the next topic of hydrogen embrittlement. Hydrogen embrittlement is the 11th in the textbook of Professor Krauss. On page 408, the result of delayed fracture done by Professor Troiano are presented. The steel is AISI 4340. After hydrogen charging and baying, the constant stress was applied. The initial hydrogen content is around 1 mass ppm, excuse me. When the baking time is short, a half hour, the notch strength decreases to a quarter from 300 to 75 KSI. Since there is an incubation time before failure, this fracture was named delayed fracture. It had been discussed that the incubation time to fracture corresponds to the time required for hydrogen atoms to diffuse and accumulate to a critical value for a failure in the stress concentration region at the notch loop. The report was published in 1958. This means that hydrogen enrichment is a long-standing concern for steel. We know that phosphorus does not come in from the environment, but hydrogen comes in steel through corrosion. As many of you gathered here today are aware, accidents of delayed fracture are significant and famous for high-strength sports. In this case, intergranular fracture also occur. And it has been discussed that hydrogen segregation at the grain boundary and reduced cohesion are one of the main causes of embrittlement. We have shears for overcoming the hydrogen embrittlement. C1 is again temp-forming and ultrafine elongated grain structure. In 2012, we reported that TF sample shows higher strength than QT in the whole range of hydrogen content up to 3 ppm, as shown here in this figure. The result obtained in this high carbon, low alloy steel with a very low level of phosphorus and sulfur. Another series, second series, was presented by Professor Ueji more recently, 2022, which is caliber rolled pyrite and delamination. They succeeded in obtaining specimens large enough to perform various mechanical tests, even after a very, very large strain of 88% cold loading. Then they investigate the notch tensile strength with this specimen dimension, and shown the left figure. They found that notch tensile strength with hydrogen is much higher than that of TF and QT magnetic steel that's shown in the last slide. What I think is important about their result is this. Delamination cracking occurs at notch root, as shown here in C. Please look at EBSD inverse pole figures in A and B, where delamination cracks propagate along pyrite block boundary, namely the boundaries between the red and blue region shown in B. This delamination should be reducing the stress concentration at the notch root, which is good for hydrogen enrichment resistance. This brings me to the idea I think you all know what my idea is. Yes, my idea is P-assisted delamination for delayed fracture. In this study, we used same SEM440 with two different P content. In this study, only two levels of P, 0.001 high purity one and 0.093 mass percent is the highest P content. The temp-forming process is exactly the same as that of the first half of my presentation today. This is the experimental method used to evaluate the hydrogen enrichment susceptibility. It is the SSRT third we always use. First, hydrogen charging for 164 hours with these solutions with various current density. A second, slow strain rate test was performed at cross-head speed of 0.005 millimeter per minute. Finally, we did thermal desorption spectrometry, TDS, at heating rate of 100 degrees Celsius per hour. Hydrogen absorbed up to 300 degrees Celsius was regarded as diffusive hydrogen 8D, which caused hydrogen enrichment. This slide shows the result for the notch tensile strength versus diffusible hydrogen content. In low PQT steel in black, the notch strength decreases from 1800 megapascal to 400 megapascal as hydrogen content increases like this. The notch strength of high PQT steel in blue is lower than that of LPQT steel black. However, high PTF temp-formed steel in red show higher notch strength than 2QT steel. The strength is still higher than 1000 megapascal, even at high hydrogen content of 3 mass ppm. This is the result of SEM fractography of QT sample. In QT, 0.093% P steel, grain boundary fracture was observed at crack initiation site, even without hydrogen charge. On the other hand, in QT, 0.001% P steel without hydrogen charging, although it isn't shown here, dimple fracture were observed in all regions of the specimen. As hydrogen content increased 1.4 and 2.5, the ratio of quasi-cleavage fracture and intergranular fracture at the crack initiation site increased as shown in D and H. This is the result of SEM fractography of TF 0.093% P steel. Interestingly, delamination was observed even without hydrogen charge, as shown in A. Delamination was then accelerated by hydrogen charge, as shown in C and D. This is a G, excuse me. This shows the detail of a delamination cracking at the notch root. The portion shown by B in A was cut vertically and observed by SEM like this. It can be clearly seen in B. Here is a notch root. Here is a notch root. Delamination has occurred near the notch root, like this. And as you can see in the magnified images in C and D, the delamination propagates along the grain boundary. Therefore, we are concerned about the elemental segregation at the grain boundary. Next, I show you the STM elementary maps. Grain boundary segregation of manganese, moly, and phosphorus are clearly shown. I believe it is clear that phosphorus segregation at the grain boundary is related to delamination fracture because of loss of cohesion. However, the effect of moly and manganese segregation are still under discussion. Now, at this stage of my talk for the second topic, you may all have this question, Q5. What are the hydrogen intrusion property of TF steel? This is very, very reasonable question since it is essential for discussing hydrogen embrittlement resistance of a steel. To answer Q5, we performed the immersion test to evaluate hydrogen intrusion. The test was done at 30 degrees Celsius with a solution here. This condition is simulating the atmospheric corrosive environment in Okinawa, Japan. The hydrogen content is lower in high P steel, 0.093% P, indicating that the P doping is effective to suppress hydrogen intrusion. I believe this is this is the maybe due to the intergranular segregation of P. Now, let us examine the relationship between the amount of hydrogen intrusion from environment, left figure, and the notch tensile strength, right figure. Even if we take a safety factor of 5 for hydrogen embrittlement, hydrogen intrusion, namely 0.5 ppm HD, a design structure of 1500 MPa can be used for HPTF steel. Of course, further research is needed, but I think this design guideline is very interesting. Now, the tentative conclusion for HE resistance. Answer to the question in the introduction. Can you make the steel tougher by phosphorus? Should be, yes, we can. We can make a steel stronger and tougher by phosphorus through delamination toughening in ultrafine elongated grain structure. This is again the case study of positive use of an embrittlement element of phosphorus in steel through microstructure control. Let me introduce briefly the related Japanese steel research project before making concluding remarks. There are 2 projects that I wanted to introduce. The first one is JST CREST creation creation of an innovative function of intelligent materials on the base of element strategy. The research period was from 2010 to 2017, completed project. And the research supervisor was Professor Kohei Tamao. In this CREST program, there was a research project entitled Light Element Strategy in Advanced High-Strength Steel, and the leader was Professor Tadashi Furuhara. The aims were to create new principles in the design of high-strength and high-ductility toughness in steels by understanding the fundamental functions of alloying element. One of the tasks was the use of localized alloying element at defect and important factor solute defect interaction. In this research task, I have performed the p-doping study to improve impact toughness that I presented today. I thank our leader, Professor Tadashi Furuhara, and all team members for their cooperation at the time. This is the other representative output of CREST project except for the p-doping study. I will not explain the content here, but will leave it on the video slides for your reference. If you are interested, please take the time to watch the video later. This is the second related research project. This is the next project, and the project title is a Research Initiative of Structural Materials for Extreme Environment, RISME. The research period is from 2023 to 2031. And the project director is Professor Kyusuke Yoshimi. The final goal of the project, I think, is structural material DX with database construction. To achieve the final goal, 3 material challenging here, have been established now. And one of 3 material challenges is hydrogen-resistant high-strength steel. And the team leader is Professor Hisao Matsunaga, Kyushu University. The second p-doping study we presented today was done as the work of this material challenge. I thank Professor Yoshimi and Professor Matsunaga and all team members for their collaboration. This is one of the distinctive activities of this project. Collaboration with industry, academia, industry, consortium for utilization of RISME data. And there are 17 companies in total now. Please go to the RISME website if you are interested. Now, this is the time for concluding remarks. As one of the concluding remarks I would like to make, here I'd like to mention the most interesting future research for me. That is, so since the delayed fracture experiment of TF material was done only with 0.093% P steel. So I have a question and interest. how does the delayed fracture strength of temp-formed material changes with the P content? In closing, I'd like to present my message again. Phosphorus, an enrichment element in steel, can also be used as an effective element if the microstructure of a steel is controlled. Thank you for your kind attention. That's all.
Okay, thank you very much, Dr. Tsuzaki. And it was very interesting and suggestive presentation on the steel strength and toughness. So now the webinar is open for discussion. So does anyone have any questions for the presentation? Please raise your hand, use raise hand button or type your question or comment in the Q&A box. Okay.
千山先生。
Yes. Kubota sensei, please.
Thank you very much. Tsuzaki sensei, thank you very much for your very, very interesting talk on the P-doped steel. I have a question. So in your experiment, the microstructure is controlled by the thermomechanical treatment.
Yes.
But also the loading condition is also controlled. So specifically, the loading direction is controlled to achieve good results. If the lamellar material receives a loading along lamellar direction, what happens? I expect the toughness is significantly reduced. Am I correct?
Yes, you are correct. Absolutely. This is the anisotropic microstructure.
Okay, thank you very much.
Yeah. Actually, if you tensile the specimen along TD or ND direction, okay, I mean series, okay, connection on the band, phosphorus band.
Yes, yes.
So specimen fractures just after yield point, very brittle.
Okay,
Yeah.
okay. Thank you very much. Thank you.
Yeah.
And also, today, your talk is primarily related to impact test. But how about the fatigue properties of this material? Is it also improved?
Fatigue material, yeah.
Mm.
So Professor Kubota, so I'm sorry, but I can't remember completely. We did some research on fatigue.
Right.
As for the well, I should check it again. So it is something different. An effect of a microstructure for the fatigue limit region. I mean a low stress region.
Yes.
And high cycle fatigue and
yes.
low cycle fatigue. The effect is different. So then, yeah. And also I should say that we haven't published the fatigue property of P-doped samples. But we did the study of fatigue on ultrafine elongated structure processed by warm temp forming.
Okay, okay. I understand. Thank you very much. My question is out from today's year topic. Thank you very much.
Yeah, and I show you. Yeah, so I understand your interest, and it is also our interest. So the fatigue test of elongated grain structure or lamellar structure is under under the study, under the experiment. Okay, so then you may see the very nice result in future, maybe.
Okay, I hope. Thank you very much.
Yeah.
Thank you very much.
Okay, thank you, Kuwata-sensei. So is there any other questions from audience? So may I ask one question? So I'm interested in the fracture surface, morphology of fracture surface of the ultrafine elongated grained steel. So I guess that the flat surface of the delamination should be brittle fracture. Is it right? So how about the morphology of the fracture surface perpendicular to the rolling direction?
Okay.
I guess dimple fracture is caused on the surface.
Yeah.
Did you observe the fracture surface perpendicular to the rolling
yes.
direction?
So there is the zigzag up and down fashion on the fracture surface like this. For instance, let me see. This is the fracture plane along to RD direction. Okay.
Yeah.
Direction of elongated grain.
Okay.
However, you can see that these steps, right? Right. So on these steps, okay, you can see dimples in some portion. Or let me see. EPMA mapping. No, not here. This is here. Let me show the case of impact toughness or light. So then, see, here, there is a step, right?
Yes.
Impact toughness. Go back. Yeah, something like that. So here's another step here, right? So, but Professor Tsuchiyama, please understand that the texture is 110, parallel RD, deformation texture. Okay, rolling direction, you have 110. So no 100. Okay.
Yes.
All right. No cleavage plane. Normal to RD. So the all plane normal to RD are ductile. Okay. So then yeah. So then of course there are some cleavage fracture surfaces in these steps also, but in some part we can see dimples.
Yes, very interesting. Even in the high phosphorus steel.
Yeah.
Very interesting. Okay, thank you very much. So is there any questions? Any other questions from audience?
So if no question, but Tsuchiyama Sensei, please look at this, right? You can see this?
Yes, I can see.
Right. So at elevated temperature, no delamination occurs. Okay, no delamination occurs
At the high temperature.
at high temperature.
High temperature. Yeah.
Yeah, high temperature. Okay, so this is because of a ductile plane normal to RD.
Ah.
And also turbine arrangement. Turbines are along
Yes, I see.
RD,
Along rolling direction.
rolling direction.
Rolling direction.
Well, I should say on grain boundary, the grain boundary are parallel to rolling direction. So that is another reason for high impact energy at this stage.
Okay, I see. So I understand that the not only grain size but also texture is very
Texture is
important
important.
in the toughness of this steel.
Yeah.
Okay.
Yeah.
Thank you very much.
Yeah, you're welcome.
Okay. Any other questions? No. So if there are no further questions, so I'd like to close this webinar. So thank you very much for very nice lecture today, Dr. Tsuzaki. So next time, I hope you come to Kyushu University, and I want to hear of your lecture by face-to-face meeting. Okay, next time.
Okay, thank you very much. Okay, thank you very much for your kind invitation in advance.
Yeah, thank you very much, Tsuzaki sensei.
Okay, thank you.
Thank you very much.